Thank you, everybody. Good morning. Assalamu alaikum and namaskar and zdravstvuyte. I'm very happy to be here, and I hope you enjoy the lecture a little bit. If you see on my title slide, I always put the oil price. You can see the oil prices are sort of fluctuating a little bit, and the gas price. And also notice here that the Texas oil and gas production curve here. Texas produces more oil than any Middle East country right now. Texas only, except Saudi Arabia. And the United States produces more oil and gas than any other country in the world. So that's a little introduction. We'll talk about chemical flooding. Here, I like to show this picture of our dear president making fun of the oil and fossil fuel people. Okay, it's good to know your president. Here are my concluding remarks. You've never seen this kind of lecture before, probably, that I'm giving you my concluding remarks right in the beginning, in case you have to leave or go to bed again or something like that. Now, I have 60 years experience in EOR, as Meyer said a little while ago, but 40 years I worked on chemical flooding, lab work, modeling, and especially field projects. I worked on quite a few field projects with Marathon Oil Company. So based upon that, I'll say that chemical flooding is not economic, at least in North America. Okay, you'll see that in China they're doing it, but our economics are different. Now, the other thing is this: all chemical flooding processes are complex. They're very complex, in fact, and they are really good subjects for experimental work, theoretical research, and for writing papers and theses. But here is the last one: do not do a chemical flood in the field if you want to make money. If you want to just do it because you have extra money to throw away, or maybe you want to do research, that's fine. But do not expect to make money. And I'll try to explain all that, why I'm saying that. I'm giving you some valuable advice upfront, okay? Now, this is what I'll talk about. I don't want to read through all that. Some general comments on oil recovery, a little bit on surfactant, alkaline, micellar flooding, ASP, alkaline, surfactant, polymer flooding, and a bit on scale up. I won't go into numerical simulation, although we've done an awful lot of work on that too. Myself, my students, and my associates, we have published easily 70, 80 papers on chemical flooding, maybe close to 100. And if you see the literature, there are several thousand papers, close to 5,000 papers on chemical flooding. Now, first we'll say a few words about some basic aspects of oil displacement, what I call principles of oil recovery, mobility ratio, mobility ratio, and capillary number. Mobility ratio is commonly known in all the petroleum courses, they cover it. Maybe you haven't seen capillary number, which is mu V over sigma. Mu is the displacing fluid viscosity in poise, not in centipoise, be careful. V is the velocity, Darcy velocity, and sigma is interfacial, or centimeter per second, and sigma is in dyne per centimeter. This is the mobility ratio graph, which is very useful. This one, sorry. What I have, this is just Buckley-Leverett calculation. You know Buckley-Leverett? I'm sure all of you know that. I used to know both of them, as a matter of fact. So what you see here is the displaceable oil versus the mobility ratio, 110, 100, 1,000. 1,000 is very, very high. And you see three curves here. The lowest one is 1 pore volume injection, second one 2 pore volume injection, third one 3 pore volume injection. So for example, just one quick example, if the mobility ratio is 10 and you inject just one pore volume, which is this black curve, then the recovery, the displaceable pore volume will be approximately 0.62. So it's a very valuable technique. Buckley-Leverett is one of the 4 very important things that I tell the students to learn before they leave the university. So Buckley-Leverett will give you that. Now, this is the capillary number curve. We have done now many measurements of capillary pressure and the residual oil in our lab. And this is just one portion of a large curve, actually. We have maybe close to 100 curves of residual oil and the capillary number. You see the capillary number of 10 to the minus 7, 10 to the minus 8, 10 to the minus 7, 10 to the minus 6, 10 to the minus 5. 10 to the minus 7, as you see written here, corresponds to a typical water flood. So in a typical water flood, you'll expect the residual oil saturation of about 0.35. To increase you increase the capillary number to, let's say, 10 to the minus 4 by 3 orders of magnitude, 1,000 times. And then the capillary number will be 10 to the minus 4, and your residual oil will be about 0.17 or 17%. So you can see that you have to increase that capillary number we had a minute ago, mu, v over sigma, by a factor of 1,000 to recover half of the oil which is left after a water flood. Okay, everybody does a water flood. Well, water flood is normally applicable, but sometimes it is not, but people do it anyway. So if you want to recover half of the oil left after the water flood, you need to increase this number by 1,000 times. And of course, that 1,000 or 10,000, whatever the number is, will depend on this capillary curve, which you must determine for each rock sample. And how you determine it, we don't have time for that, but it can be done. It's a very lengthy and tortuous experiment. How do you reduce interfacial tension? Well, the obvious solution is that you use surfactant. So if we have a surfactant, and this is a log scale, and this is a log scale, and this is concentration, and this is IFT, interfacial tension sigma, and this is something like 10 to the minus 6, okay? And the concentration, let's say here, is about 0.1. Then you get a curve like that. So you have to determine in the lab. It's a expensive and time-consuming job. Now that is fine. You come up with a number. You say that, okay, the concentration of 0.1 will give me a low enough interfacial tension to have a high enough capillary number. That is nice and good. The only sad part is that this curve shifts at time. We've done this in the lab over a period of a year, and the curve keeps on shifting, as you can see. And so your original determination is no longer good. And also the concentration also changes because of adsorption and other interactions with the rock. So it's a very difficult thing to have a low enough interfacial tension for a long time. Another way of doing it, which is really not the subject of this talk, you'll see that later on in the next lecture or the one after that, is that IFT is also a function of temperature. Now this is not a log scale, regular scale, and the curve comes out to be like that. And this is 0. So at a high enough temperature, you can get an interfacial tension of 0 between the aqueous phase and the oleic phase. What does it mean? It means that the oil and water will mix completely, they will be miscible. Okay, so that is a different matter, but I wanted to mention that. Now let's look at before we go into look at the EOR methods. If you attend the next talk, you'll see this diagram again. Lots and lots of enhanced oil recovery methods. But the sad part is that very few of them are commercially successful. That is the key number, key word here, that we want commercial success because we are in the oil business to make money. Okay. If you say that where our oil production price is $100 a barrel and the oil price is only $50 a barrel, that's no good. Okay, so many of these methods will give you additional oil. You see here non-thermal methods and thermal methods. And the circle method that with the red circle are the only ones which have been commercially successful. Among the non-thermal, maybe some polymer fillers, you see the square here, and maybe enriched gas drive, and among the gas drives have been commercially successful. But all of these methods have been tested in the field and they are being done again and again and again. In the United States, for example, we have done more than 500, at least that many I know myself, 500 surfactant fillers. How much oil did they produce? Nothing. All the people will disagree with me. So that's the size of it. So I want to show you that there are many EOR methods, and the ones which have been commercially successful are shown by those red circles. We are talking about in this presentation about non-thermal chemical fillers, which are these here. You'll see those names again. Now, in passing, I'll say this too, that non-thermal chemical methods have been used also for heavy oil recovery. And you see here water flooding. Water flooding in heavy oil recovery is very, very inefficient, but economical. You still make money. Not a whole lot, but it's not, you don't lose money. I have a lot of experience with water flooding heavy oils. Polymer flooding, surfactant flooding, alkaline, emulsion, immiscible CO2, solvent, and their combination, they have all been used and they're not successful for heavy oil recovery. Okay, so I wanted to get this out of the way up front. One of the very serious problems with surfactant flooding, any surfactant, and also with other chemicals is adsorption. How much is the surface area of a rock? Here is a barrel. Now we can calculate this. Here is one barrel of oil or anything. A barrel has a volume of 5.615 cubic feet. It's not a whole big volume. Suppose you have a size, a rock, a rock now, I'm making it to a sandstone, let's say. You have a piece of rock size of a barrel. What is the surface area inside the pores of that barrel of rock, worth of rock? 2 football fields. Do you know the size of a football field? If you don't, then look it up, okay? 2 football fields. Many years ago, I went for an interview, and this is the question they asked me, is what is the size of a football field? So be prepared for it. Anyway, so here you have a piece of rock, size of a barrel, 5.615 cubic feet. The surface area in this barrel is 2 football fields. So whenever you're injecting any chemical, anything in fact, you keep in mind that it's being spread on 2 football fields. Adsorption of surfactant and other material, alkalis, everything, all the chemicals, ranges between 1 and 20 milligram per gram of rock. It can be less, it can be even 0.5 and so forth. The rock surface that I just described, you can also say that it's about 1 square meter per cc of rock. Have you seen a sugar cube? A sugar cube, what is the volume of a sugar cube? 3 cc's. And 1 square meter becomes then 3 square meters. So imagine that a sugar cube has a surface area inside it, which is almost like 3 screens of a typical slideshow. So that is one of the key factors to remember, that you're dealing with very large surface areas, and whatever you're injecting must contend with that area. Now, here is a little calculation. You don't have to do it or anything like that, but I'm just showing you that suppose the absorption is 5 milligrams per gram. What is the amount absorbed in the rock in a 10-acre, 30-foot thick, 24% porosity pattern? Do you know how much it is absorbed? 8.6 million pounds. So when you design 10 acres is not a very large area. Actually, in chemical flooding, when we do a chemical flood, I worked on many field projects of chemical floods, and our areas were normally not 10 acres, 5 acres, because we had no control on 10 acres. So this is the injection well here. But even then, you can see that it's a gigantic amounts of the chemical that you're losing to the rock. And then you have to inject more chemical, because after all, you need chemical to do whatever you want to do with it. Maybe you want to reduce the interfacial tension. So maybe the injected chemical is twice that much. So this is one thing to keep in mind. Now, there's another very important matter of salinity. Salinity has important effect on many chemical floods, chemical processes. You know, in Pennsylvania, at Penn State, I worked on salinity in the context of alcohols. Would you believe that in Bradford in the early 60s, 60 to 63, we did an alcohol flood to reduce the interfacial tension, because the idea was that we don't want to inject a solid material like a surfactant. So it's a long story. I did a lot of work with alcohol and different salts, and then much later, Nelson at the University of Texas worked on you see the reference on this slide here. This is his paper in 1982. I worked on it in 1960 to 62 period, 20 years before him, but he never referred to my work. Oh, I have nothing against it, that's fine. But what he showed and what I showed is that salinity requirement of a chemical, I'm looking at the third one here, okay, because we don't have time to read everything. This one, salinity requirement, what is that? For a given chemical flood, whether it's a surfactant or whatever kind of flood, there is certain salinity that you will have to have for the flood to be successful. Apart from, I'm not talking about absorption. Absorption have to always keep in your mind, a barrel of rock is 2 football fields, and you're throwing all that liquid you're injecting on 2 football fields. So he came up with this salinity diagram. Actually, we came up with this much before him. Actually, there were people at Gulf Research, it doesn't exist anymore. They were working also on it, and I worked with them. So here is a typical diagram. Look at the diagram, right, this one here. We have a surfactant, we have brine, and we have the oil. So given that, we can draw this binodal curve. So I determined in the lab maybe at least 200 binodal curves for different systems. So this is the binodal curve. And there's the flat point. Flat point, I don't know whether you've done these things in your courses. Flat point is where the compositions of the oleic, which is this phase, and the aqueous phase become identical. And these are tie lines that you see here. So these ternary diagrams are at the heart of chemical flooding, depending on what process you have. So myself and people at Gulf, at about the same time in 1962, they came up with this, that there are 3 kinds of system. This is the first system. Later on, Nelson called it type 2 minus. We just said flat point to the right, and this one, the other one, the flat point to the left. And then it is still another system with two binodal curves and a triple point here. So we came up with this long time before Nelson. This is how Nelson's diagram. Here is very hard to follow. You have to read this paper to understand what he is doing here. But it's a useful diagram because it will tell you how you can distinguish the three phases that we saw in the ternary diagram in the middle, based upon the chemical salt concentration and surfactant concentration in the x-axis. So salinity is a very important factor in all chemical floods. Okay, then alkalis also enter into many floods. Ideally, sodium carbonate is a good alkali. We call it best based upon our experimental work. Then potassium hydroxide. But what we normally use is sodium hydroxide. Why? Because it's cheap. So caustic soda is very cheap. I don't know what's the price, but when we were doing these experiments, the price of caustic soda was about 60 cents a pound. Okay, so if you use an alkali, well, the alkali will adsorb too. Remember, I said in the beginning, keep that in mind. But you have worse things happening because alkali will also react with the minerals. What are the minerals? All the clays are minerals. And also, if you're lucky and you have some alkali present, there will be entrapment, entrainment, and wettability reversal. Oh, there's no time to go into all that, but these are the mechanisms by which oil is being produced. All this is wonderful, but it doesn't work. I'll show you that a little later. Now, typical micellar solution. Now, I'm giving you all the basic concepts: adsorption, salinity, and then I talked about alkali. Now, a little bit about microemulsion and micellar solution. Same thing. A micellar solution, if you put it in a glass of water, will look completely clear. You won't say it's an emulsion or a microemulsion. It's so small drop size. It's 10 to the minus 4 to 10 to the minus 6 millimeters, okay? And typically you'll have a hydrocarbon, you'll have water, a surfactant, and then a co-surfactant, which will be an alcohol and a salt. And then depending on these compositions and the type of oil, you can have either kind of solution. As you see, I've shown you just one micelle here. If you see the title cover of this talk, I have given a diagram like this there also. So here's the surfactant here. This black part is oleophilic. Philic means liking. And this clear part is oleophobic or hydrophilic. Okay, so you can have this kind of, depending on the surfactant, depending on the oil, you can have either kind of a solution. So we did this sort of experiment in the lab many times over a period of 20 years to support the micellar floods of marathon oil. Now here's a diagram from my own papers, old papers. Would you believe that this is the diagram which shows the so-called chemical EOR target? Target, okay? I'm not saying that is necessarily the potential. So what I have done is this. I have assumed that the primary recovery is worldwide 1/3 of the oil. And I have assumed that the chemical flood will give you also another third of the oil. I mean, it's like dreaming. But if you assume that, then look at the potential. In Saudi Arabia, you have potential of 173 billion barrels. These are billion barrels, okay, 10 to the 6 barrels. Well, the scale says that here, billion barrels. So look at the potentials, huge potential. If you have a successful chemical EOR method, which doesn't exist at this point. Okay, what is the right now the status of chemical flooding? You see this graph here. Well, this is an old graph because nobody publishes much data on chemical EOR production. But I can tell you, in USA, the chemical flood production for 2017 is this, 0, based upon the oil and gas survey. Okay. In China, in a particular area called Daching, you'll see a little bit about that also. In Daching, there is a polymer flood. I've been to Daching 3 times and I've seen this polymer flood. They are producing right now 170,000 barrels per day. And they have 7,000 wells in this field. I saw it, as I said, 3 times. So currently they are producing 170,000 barrels per day from 7,000 wells, and they're using a very high polymer concentration. And it's fine for China. You know, China has to import 8 million barrels a day, huge amount of oil. And so any oil they can produce is fine, although I don't see how it could possibly be economic. So that's why we don't do that. In the USA, we won't do anything which doesn't make money. And well, we may do a research project, but a field project has to make money. And we did try, you can see from these, but the highest we ever produced in the mid-60s, mid-80s by polymer flooding was about 20,000 barrels a day. Right now, there's nothing. There may be a small project here and there, okay? If you talk to the people at the University of Texas, they will tell you, oh, there are several floods, but they won't tell you where. Now, let's say we are short of time, but we'll talk briefly about chemical methods, and I'll talk about alkali, polymer, surfactant. I'll skip emulsion, and I'll talk about micellar and ASP. So a little bit shortened here. What is the objective of a chemical flood? Well, produce oil, of course, but technically what we want to do is to make the capillary number large. You remember that curve? We also want to decrease the mobility ratio and maybe want to emulsify the oil. If you emulsify the oil and produce an emulsion, remember that you have to break that emulsion too, which is not a cheap process. That's another matter. General limitation, the main ones are the dark ones, cost to the chemical. All the chemical cost money. Gravity segregation. Anytime in any process, chemical or thermal or whatever, remember the heavy stuff goes down and the light stuff goes up. Not a very profound thought, but amazingly, so many people don't know that. They keep forgetting it. And the other thing to remember is geology is unforgiving. What is geology? I could talk about that whole day. Geology is unforgiving in many recovery methods, especially chemical flooding. What does it mean? It means that if the structure is such that your chemical slug won't go evenly, it will break up very quickly and you'll have nothing. Well, I've seen several chemical floods in my own experience where we produce exactly 0 oil. In fact, in some of them, the original oil production went down when we finished the flood. Now, let's take a quick look at different recovery methods. Polymer flooding has been used more than any other process. In the US, maybe we have done a few thousand polymer floods, and some of them produced a little bit of oil. The main problem, there are many problems with polymer filtering. The loss to the rock by adsorption. We already talked about loss of injectivity because polymers are large molecules which stick to the rock and hinder the advance of the fluid. There is a lack of control. This is the worst problem because of geology. High velocity shear. And often we apply it very late in the water flood, which doesn't make any sense, but people do it. And people keep doing it. You remember Einstein's famous quotation, doing the same thing over and over again and expecting different results is, and I'll leave the rest. One of the key things in polymer filleting is the resistance factor RF. RF is a way to reduce the mobility ratio, make it more favorable. And you can determine it by a rather simple experiment. I won't go into that. You can get the resistance factor. There are equations, or you can do a simple vertical flow experiment and so forth. So there are curves of polymer concentration and RF. So you'll see curves like that. This is the resistance factor here. And this is the polymer concentration. And you see the resistance factor will go like this. So that is fine. You have to be careful where you choose the concentration. But the sad part is that this is also time dependent. So you really need to do this experiment over a period of a year. And we did that. Now, we already said a word about that. If you're doing a water flood and the water flood is doing badly, in other words, the water oil ratio is going up, then people say inject a polymer. Where will you inject the polymer? Early, late, at the end? And all I want to tell you is that if you inject polymer late in the water flood, it doesn't do any good. Oh, well, the polymer manufacturers are very aggressive people. They will tell you, oh, you can inject a gel. Sure, you can inject a gel. But I wrote here, one of my friends, Chef, he said that late in the water flood, you can use a polymer gel. Well, gels are very viscous, not very easy to inject it. Polymers have basically three applications: mobility control, profile control if you have several layers. Now, I designed a very big project on profile control in Catril Este in Argentina. Oh, we spent many, many millions of dollars on it, and we produced 2% oil, 2% additional oil. They did this project in spite of the fact that I told them initially not to do it, but they did it, and there were 7 layers like that. And we produced 2% oil. We did a lot of work on that. Now, there are 2 kinds of polymers: polyacrylamides, which are chemical polymers, and biopolymers, which are essentially made by bacteria. The main difference is that bacteria, the bacterial biopolymers can stand a higher salinity. Some of the reservoirs have very high salinity, like the reservoir in Saudi Arabia has a salinity of 30% by weight of salt. 30%, okay, 300,000. Polyacrylamides are desirable because they have good viscosity control in fresh water, but they're no good for high salinity or high temperature. Although I must say that the companies are making newer and newer polymers, and this Daqing field I mentioned earlier in China, they actually manufacture their own polymers. One time I went there and they gave me 3 big sacks of polymers. And when I came to the US, the custom people took them all. But they have also problems. They're stable up to about 160. But the Gawar field, for example, in Saudi Arabia has a temperature of 215 degrees Fahrenheit. Nevertheless, there are polymers which can stand that temperature. And there are other factors that you can read on the slide. Biopolymers will give you a good viscosity control in fresh water and also in high salinity. That's the only good thing about biopolymers. Otherwise, there are nothing but problems with the biopolymers from my experience because of the residual bacteria in the polymer. You'll see that you plug up the formation. Laboratory testing, rather simple tests. Some of them are very tedious, and some of them are time consuming because you have to do it over a period of a year. I know nobody does that. We did, however. That's how we know that these things are strongly time dependent. Also, you can use horizontal wells, which will give you a little better control of the advance of the polymer. And people have done that, not particularly successful because problem with the horizontal well polymer flood is the profile control at the well, okay, and that is not easy with the polymer. Here, there are some case histories in the flood. Here I'm giving you an example from India. I'm from India. So you can see this Sanand field in India, and you see that we have oil production here going down. Actually, it was a water flood. And then we start polymer injection, and it went up a little bit. And you can say that the cumulative oil curve is this one, the red one, and you can say that this is the EOR oil. But what is the oil production rate? 75 barrels per day, cubic meters per day. 75 cubic meters is about 400 barrels per day. Not very much. And here I listed some of the polymer fillers. And you can see, I mean, this is a good sample. You can see the recoveries, 8%, 10%, 30%, highly questionable. But most of them are 1%, 2%, something like that. And that won't pay the bill, I assure you. 30% is totally improbable. In any case, in case you want to find it. So there's a summary for you. Now we go to surfactant flooding. Surfactant flooding, I told you that the main problem is the adsorption of the rock. And the other problem, which is also very important, is that the slug that you inject will dissipate as it advances into the rock because of dilution and because of the simple fact that you have slug expanding, and so it's becoming less concentrated, and dilution by water also. So surfactant flooding has not been successful. Again, if you go to our friends at the University of Texas, they will tell you, oh, there are successful surfactant floods. Okay, if there are, show me. Here are a couple of examples of surfactant floods. You will find quite a few in the literature, and they all claim high oil recoveries, the 10%, 14%, 10%. Well, I know several surfactant floods firsthand where the recovery was exactly zero, nothing additional. Here is an example of a surfactant flood which was successful, supposedly, Glenpool in Oklahoma. And you see the oil production went up supposedly from something like 100 barrel to 1,000 barrel, and then it dropped again. So when I see something like that, I say to the people involved, I say, why didn't you continue that? Why didn't you expand this flood over the entire field? This is only a small portion of the field. And well, they don't give me a good answer, but the answer is very clear because it didn't even make any money. Money making is the main thing we do, okay, in the oil business. Otherwise, we'll do something else, a grocery store. Alkaline flooding. This is the most undesirable process. Never do it, okay? I have a lot of experience with alkaline flooding. The idea of the alkaline flooding is this, that you take an alkali like caustic soda, okay, or anything else you want, and the oil basic components will react with this alkali acid components of the oil will react with the alkali and make a soap in place. And this soap or surfactant will do all the wonders that we just discussed. It just doesn't happen because the alkali doesn't easily mix with anything. Alkali and oil. This is if you have ever lived in India near a village. Oh well, we did that too. You probably saw this. They will take some oil. This is mustard oil, okay, cheap oil, and then they will put a little caustic soda in it, and then they will take a stick and stir it for 5 minutes, and the stuff will become solid soap. So that's how the villagers in India, and we did that too in India. We used to make soap like that. This soap should not be used for washing your face, okay? But it's okay for clothes. So that's what they want to do in a pore space. A pore space is 0.01 millimeter or smaller. There is no stick to stir the alkali. Here are some data from alkaline floods. People who write these papers on these floods, they don't want to say that the recovery was zero. So they show some recovery, but trust me, it is zero. Weinbrand, one of the consultants in California, he wrote a paper a while ago. Weinbrand, you can find that paper, and he, on all the caustic floods that you could find, and he came with the amazing conclusion that the additional oil production by caustic floods that he looked at was 1 barrel per day. Well, you can get 1 barrel per day just by cleaning out the wellbore. Here is an alkaline flood history. I had to give you a history. So the David Pool in Alberta, they had a water flood, then they did an alkaline flood. So do you see an increase? Maybe you see it. That's how it is. Then you have alkaline, surfactant, polymer flooding. You throw everything together. We did this at Penn State, and one of my former students, Dr. Hilmi Sayu, who is a very prominent person in Cairo University, professor there, he did this work, among other work. He took all those three and mixed them together, and we called it sloppy slug. Much later, the other people came and they called them by different names. We also did ASP, where we had separate slugs of alkali, surfactant, and polymer. And we had other combinations you can see here. And they gave some additional oil recovery in a lab flood. Okay, now mind that we are doing these things in lab. Here is the Dacheng. I mentioned Dacheng a few times. I've been there, as I said, several times. And that's what they claim. In China, they publish an awful lot of papers. Only 0.01% of those are in English. So you don't see much of the data. But I have many Chinese friends, and they gave me a lot of data. And I'm showing you a good example where they injected ASP, alkali, surfactant, polymer, and the oil production went from 50 cubic meters a day to something like 70, 80 cubic meters a day. So in Dacheng, they have several polymer, ASP and polymer floods. Now comes the micellar flooding. As far as I'm concerned, this is the only process which has been successful based upon something like 35 field tests in recovering the oil left after a water flood. So that's the key thing. We use this process in the field after the water flood, always with residual oil. And the process is very complex. Here you see an oil bank in this picture here. Here you see the micellar slug, which is maybe 5%, 6% pore volume. Why so small? Because it's extensive. Then we have big polymer slug, maybe 50% pore volume. So we inject all those slugs and we recover some tertiary oil. These chemical color selects is costly, and you must use a small well spacing. This is one of the key things in all chemical floods. And I'll show you now some. Here are some lab data where we are comparing an ASP flood and micellar flood. And the main thing is, well, they were the recovery by ASP. We chose our best ASP flood. It gave us 80% tertiary recovery, and the micellar flood gave us 92%. Here is a Bradford. Bradford is, I lived close to Bradford for many years. They did a huge field test and they recovered some oil. It was not economic at all, but they did it. This is a very, very useful diagram where we have cumulative recovery versus the slug size. And the beauty of it is this, that we have shown the lab curve and the field curve. So I'll just take one quick example. Henry was one of our big, when I say our, I mean myself and Marathon and others. So Henry was one of the big and successful field tests. And the field curve, the field point, I've just put one point, is this point. This is the recovery in the field. And the recovery in the lab is this one here. In the lab, we had many selects, so we can plot that curve. But in the field, we had only about 50% or so recovery. In the lab, we got as much as 100% recovery. So why is that? Well, the lab tests, one and all, even the work which our friends at University of Texas do, is not scaled. We are the only people who did a scale up of micellar flooding. I'll show you a little bit of that. We are running out of time. Here's a comparison of the field tests of ASP and micellar flood. The top one is the ASP, the lower one are the micellar floods. And you can see for yourself, micellar gave usually higher recovery. Some gave lower recoveries too. So ASP and micellar have produced oil in the field, but they are not economic because you have to use very small pattern sizes. There are other chemical methods too. I won't go into that. None of them works. Reason for failure, many reasons. Well, one reason is low oil price, but there are technical reasons, there are geological reasons, heterogeneities, for example, or you can have fractures. And the most important is this one here, in red. Inadequate understanding the process vis-a-vis rock properties. You are going to do let's say, a micellar flood in a reservoir, and you haven't tested that particular slug for the minerals in that particular rock, that is the problem. So that it won't do any good, even if your pattern size is not a problem. So scale-up methods, we do a lot of scale-up. Scale-up means that you derive the scaling criteria and then you scale the models, lab models. Here, for example, a very quick example of micellar flood scaling. These are the groups you must satisfy in the lab and in the field. And then the lab results can be upscaled to the field. Here is an example of the actual lab experiment, which is the black curve, and the field experiment, which is the red curve. So we have these methods for scaling up micellar, but we didn't develop methods for the other chemical. We are working on some of it. Chemical in EOR for heavy oil, don't bother to do any chemical flood in a heavy oil reservoir. Offshore, what do we do offshore? We have very little space on a platform, we cannot do a whole lot. So offshore chemical EOR, people have done it. I know some people in Brazil did it. Didn't work. Improved chemicals are being made. Now, if you talk to my good friend Gary Pope at the University of Texas, you can see his lecture on the internet. He has 150 slides on chemical flooding, and he says his main pitch is that new chemicals are coming, new polymers are coming. Of course, they are coming, but they're not cheap. Here are the screening criteria for chemical flood. I don't have time to read through those. You can look at them. One of the important things to look at is that you must have high enough oil saturation to make it worthwhile. Here is the number, at least 600 barrels per acre foot. I can do an economic calculation in 5 minutes to show you that even that won't make any money if you recover it all, 100%. How to plan a flood? Long process. In Argentina, that Petrel flood, it took us 5 years to design the flood, 3 years to run it, and they recovered 2% of the oil. Process evaluation. After you do the flood, what do you do? Lot of things to do. You do a post-mortem, as they say sometimes. Take a lot of course and see what went wrong. We did this too in marathons projects. And then interpretation of the results. How do you interpret the results after you do all that coring and everything? Cost of the chemicals. All these chemicals are expensive and they keep changing. Cheaper chemicals are coming. How many chemicals can you try? If you just choose one polymer, just one polymer for a polymer flood, it will take you a year to test it out thoroughly. But you won't want to test one. You maybe want to test 5 of them to see which one is cheapest and best. So these are the kind of problems you have. Now, people have a case for chemical flooding. They say, well, we will be leaving in the reservoirs 2 trillion barrels of oil. What do we do? How do we recover it? Well, we have ideas. Chemical flooding is one of them that comes to mind very quickly, and you do a chemical flood, gives you 5 years lease on life, and then after 5 years say it didn't work. Maybe you should do another one with a new chemical. So that's how things go. So what are my conclusions? That we have now valuable insight because of all the failures in the past. Micellar flooding and ASP hold the greatest potential. Okay, but neither of them has been commercially successful. Our friends in China will disagree. They will say, no, we are making money, but their criteria are different. What we should do now, we should reevaluate all the failed projects. But nobody likes to write papers on failed projects. You have to beg companies to give you data. And my concluded remarks, once again, that you saw right in the beginning, if you had the patience to listen to all this, that based upon my experience, chemical floods are not economic. All chemical flooding processes are complex. They are really good for lab work, experimental work, simulations. You can write lots of papers. There are many thousands of papers on chemical flooding, not counting the Chinese papers, which are in hundreds of thousands. And you could write a nice thesis on it. Hilmi Sayyid did. His thesis was on micellar flooding, one of the best theses we produced at Penn State. But do not do a chemical flood in the field if you want to make money. Okay. So that's my whole talk. I took a little longer than I planned to take. Thank you all very much.